I know.
Okay, so today's objective here, everybody, is we are going to go to the mathematics symbolic side. So last night's big focus was macroscopic to molecular. What do we see with our eyes and how does that connect to what we don't see? Today we're connecting the full triangle because we're bringing in the mathematical side of calculating the actual values of heat. So with that hand warmer, we can actually calculate how much heat does it put out in a measurement of energy. Okay, so our first equation we're going to learn how to use is this one right here. It's on our formula sheet, so we don't need to memorize it. Just need to know how to use it. So let's define some variables here real quick. Reminder that on the formula sheet, variables are defined for you too. Right? So you don't even have to remember technically what Q is. It will be shown to you on there, but let's put it in our notes here. So Q is the symbol they have designated for the heat of the reaction. Okay, so when I do a reaction, Q tells me how many joules, so heat is always going to be in the unit of a joule, which is capital J. Okay, once again, joule is just a unit of energy, particularly for heat. Okay, M is for the mass that I tested, and it should be the total. So keep in mind, like with this, the idea of the M is obviously if I had a bigger hand warmer, if I had more mass, I'm going to get more heat. And that's always going to hold true. If you have more wood, you're going to get a bigger fire. And so that's where M comes into place. We need to know how much are we actually testing with. Okay? C is something known as the specific heat. We'll talk more about it later today. For now, no, it's going to be a constant that's given in the problem. It changes, so it's not like R where it's like a set constant. It's more similar to like K in rate laws, where it's like constant for a reaction and for a substance. And we'll talk about what it means here in a bit. Okay? And then delta T is our change in temperature. So these reactions are quite simple. The process of measuring heat is known in the lab setting as calorimetry. So doing a calorimetry experiment is a way in which you are identifying how many calories something has, aka how much energy it gives off. And it's pretty simple in the sense of you just take your substance, mix them together, measure the temperature change, and then you can calculate the heat. The one thing to consider is because we know heat, as we talked about last time, heat flows, right? Heat flows from high to low. It's always equalizing. So the one thing with the calorimeter is you need a device that can contain the heat. You need a good insulator. Because otherwise, if the heat escapes, then my thermometer can't measure it. Or if outside heat comes in, then that's going to influence it too. So a calorimeter is just a device that can contain the heat. There are a lot of ranges of what calorimeters can be, right? Simple ones to fancy ones, but it's just something that can contain the heat. So let's look at a problem here and practice plugging these things in. So our problem here says, when a student mixes 50 milliliters of a 1 molar hydrochloric acid and 50 mils of sodium hydroxide in a coffee cup calorimeter. Now what that's saying is literally what it's saying. One type of calorimeter is to use a styrofoam cup, a coffee cup. Because styrofoam is a great insulator, and so that's what we'll use for our calorimeters, are styrofoam cups. And that's what I used to call it, so I'm not even like being cheap on you. They work really well at maintaining the heat. Okay? It tells us that the temperature of the solution increased from 21 to 27 degrees, 27.5. We want to calculate that heat change. Circle or highlight this bolded word for me. Once again, if you want to use your highlighters today as we do different steps to kind of emphasize connections here, right? Of like, okay, this unit came from here, that unit came from there. Okay, assuming that the calorimeter loses only a negligible quantity of heat. Now this fancy sentence, I just want to emphasize here because it does have value. Anyone, what is that telling us, that sentence right here? Assuming that it loses negligible quantity of heat. Yeah, Brian.
It's making sure like all the heat that we're measuring
that? How else am I finish that? Yeah, it's pretty much just saying like, we're assuming the cup is perfect and it's not losing heat. Now, in actuality, they're not, and they do lose some amount of heat, and there actually is a more complicated way where you can take into account the error effect of it. But on the AP Chemistry exam, it's always going to have this sentence for you, which is nice because it simplifies the math. So, okay, it says the total volume of the solution is 100 and has a density of 1 and a specific heat of 4.18 joules per gram Kelvin. All right, so we've got a lot going on here, so let's take it piece by piece. So my first step is, all right, what am I trying to find? Q, heat change, right? So my equation for Q is MC delta T. The nickname for this equation that I learned in college is MCAT. Because if you like M, and that kind of looks like cat. And that's like the test you take for medical school, which a lot of people studying chemistry go on to medical school. So if I call it MCAT, that's just slip of my tongue. All right, so we need these three variables to plug in to find Q. So let's find each of them separately. So I'm going to put that over here. So for M, what in my problem is given that will help me get to a mass of my total cup going on here?
Polarity.
So we have molarity, that could help. What else are we given? The density, and that's going to be actually my choice. So notice they give us the density here. So I'm going to do everything for mass with my black marker. So if you want to like keep the same color here. So using this and the volume, I can get to a total mass very easily. So they tell us it had 100 milliliters. So notice there. And then since the density is 1 gram per milliliter, we have 100 grams. Questions on how I got the mass? Sometimes the mass might be given straight up. You don't have to even convert to it, but we need it to be in grams. Okay, all right, I'm going to switch colors here. So the next variable we need to find is C, specific heat, which is given in the problem. And it will be always given because it's a constant for the type of solution. And once again, in the next slide, we'll define more what this means. Okay, and then the units of it are joules per gram times Kelvin. All right, we got M, we got C. Now we need delta T. So change in temperature. So that should always be, you're always comparing the final from the initial. So my final temperature was 27.5. I can't circle that, but minusing, does it say 21? Yeah, 21. So 6.5 degrees Celsius would be my change in temperature. Yeah.
What's the symbol for the letter C?
Sorry, my J looks a little, so it's joules slash, I could write it on top of each other if that would make more sense. It's the same thing as that.
Oh.
Does that look good?
Yeah, that makes sense.
Does that make more sense? Okay, good question, Brian. I'm sure you weren't the only one. Okay, Zach.
Do we have to convert Celsius to Kelvins in order for the equations to work out?
Good. So the next thing to notice is with these weird units that we cleared up here, we need to make sure, what's the final unit we want Q to be? Joules. So J is the only unit that should not cancel out. So grams is going to be able to cancel to grams, but our temperature in this case needs to be in Kelvin because it's in Kelvin up here. The nice thing is if I were to convert this number to Kelvin and this number to Kelvin, I'd still get 6.5.
Oh, that's right.
Because Kelvin is just a shifted scale from Celsius. But since it's shifted by 273, it's an addition shift, right? If I add, so this is adding 273, add 273, right? Add 273, add 273, but then I'm minusing them anyways. it will be safe. But yes, we do need to make sure the unit matches either way, Zach. So we can point that out. Okay, questions on where I got any of my pieces from? Okay, so then let's plug it all in. So we're going to plug in 100 grams, plug in 4.18 joule per gram Kelvin, 6.5 Kelvin. Let your calculator do the work. Questions on our setup or how we found that? Okay. All right. Don't say anything out loud. I want everyone to think for themselves. Is this reaction endo or exothermic? Don't say it out loud. Think in your head. Is this reaction endo or exothermic? Is it releasing 217 joules or it is absorbing? Don't say it out loud. Think for a second, and then I'll have you show me your answer. Okay, on the count of 3, you're going to show me one of 2 signs. Okay? Now, as always, if all of a sudden you realize you're showing the opposite sign of everybody else at your table, I know it can be very tempting just to change. But I encourage you not to, because once again, it helps send a signal to me that we don't understand and I need to explain it better. And if you're feeling embarrassed, just remember, nobody remembers your mistakes like you do. I promise. Right? There was a day last term where I was so embarrassed by something. And I asked people the next day, and you guys didn't even know what happened. But I felt so embarrassed inside. I had a huge stain on my shirt.
Oh, yeah. Oh, yeah. I didn't notice.
Okay, now a bunch of people didn't even notice. But you couldn't remember until I told you your mistake, right?
Right.
So that's the thing is, people don't constantly remember your mistakes. So don't be embarrassed, just do it. Okay, so the signs are exo or endo. Okay? All right, on the count of 3, put your arms down. You got to do it on the count of 3, so just do your honest answer. Ready? So you're going to show me for this reaction, is it exothermic or endothermic? Ready? 1, 2, 3. Show me your sign. I like the ones that are like, it is exothermic. Well done, guys. That's a good sign for this one. Have a smiley face. Okay, questions on this problem before we try another one? Actually, before we try another, we're going to do this. Everybody stand up really quick. Stand up, stand up. I've been reading through your guys' reflections, and a common recommendation from some people is just opportunities to stand and stretch. I know we do a lot in this class, right? So I'm trying to do things like that. So while you're standing, what you're going to do, so with your table buddy, okay, is whoever, this one will be easy, yeah, that's what I did last week. Who's ever taller, just picking a fact, okay, you are going to, in 1 minute, quickly reteach your partner how to solve this problem. Ready? Set, go.
Calculator goes.
I bet you that was really hard.
Okay, let's take a look at. Hold on. Something's up. So, as we're solving for Q, the thing to keep in mind is Q that you find using the equation is technically telling you the heat of the calorimeter, right? Is the calorimeter absorbing? How much heat is it absorbing? Because that's what we can measure. We technically can't measure the QRXN, this stands for reaction. We can't directly measure the heat of a reaction because that heat is being used for something, right? It gets used to break bonds. And so you can't directly measure that, but because heat is being trapped and not going anywhere, whatever the Q of the calorimeter equals, it's going to be equivalent to the heat of the reaction minus the change in sign. So that's why our last problem was exothermic, but our Q was a positive number, and if you remember from last time we mentioned that exothermics have negatives in front of them to show the direction. That's why. Now, often with the solving of Q, it actually doesn't really matter the sign. Because most of the time the question just wants to know what is the value, right? What's the numerical amount of the heat? Our next step in this is we're going to calculate delta H. Delta H sign should match whether it's endo or exothermic every single time. It normally is a 2-point question, and 1 point is for the answer, 1 point is for the sign. So we'll kind of keep this, there's a little sign flip that's always going to naturally happen as we do this. Let's first talk about specific heats to understand that concept a little better, and then we'll do our next problem. So the specific heat of a substance is a measurement of how many joules it takes to raise that substance by 1 degree if I have 1 gram. So I'm going to write that definition over here as just a maybe simpler way of understanding it. So specific heat means how many joules it takes to raise 1 gram of the substance by 1 degree. So it's a constant value, but it changes depending on what you're working with. And we'll give some examples here after you maybe write that other definition off to the side there. So I'm going to draw a simple picture, but hopefully it'll maybe help in understanding. So imagine here that this cube, okay, represents 1 gram of water, right? So imagine I have 1 gram of water, which would be a pretty small amount, maybe like half a teaspoon or something, okay? This right here for water, liquid water has a specific heat of 4.18. So what this value means is, let's say that this block of ice is not, we could call it ice, I guess it's liquid water, so it can't be, it's liquid water. So let's say right now it is at 33 degrees Celsius, just picking a number. In order to raise it up by 1 degree, I would have to pay 4.18 joules. So if I put in 4.18 joules into my drop of water, it would go from 33 to 34. That's what a specific heat represents. Versus, if it wasn't water, sorry, I drew my block small, so I don't know why I wrote everything else so small. Hopefully you can see that still. Okay, so imagine now, instead of water, now I have a block of iron. A 1 gram cube of iron. So this is 1 gram of Fe. The difference now is how much do I have to pay to make it go from 33 to 34? I only have to pay 0.45 joules. So don't say it out loud. Which one's going to heat up faster? My iron or my water? Don't say it out loud. whisper with your table buddy what they think. Which one's going to heat it faster? You guys can whisper to them. That's whispering behind your back. I'm trying to decide when I rearrange the seats. We lost one person, so now technically everyone could have a table buddy. But then there'd be a table going into. So I can't decide which is better. Is it better to be in a threesome or always have a buddy? I think too, because then there's like more to like discuss. So. Okay, point. Ready? Everyone take your hand, point to the sky. Ready? Point to the sky. On the count of 3. You're going to point to the window if you think the water will heat up faster. You're going to point to the wall if you think the iron will heat up faster.
Which wall?
That one. Okay, are you ready? 1, 2, 3, point. Oh, well done. Have a smile. I guess if you're pointing to any wall, it counts. Good. Okay, does that help us understand what specific heat represents? Okay, one cool thing I want to bring up, someone asked a question last class that I thought was a cool connection. With this idea of it, do you guys remember our graphs that looked something like this when it came to heating of phase changes and things? Right, we're like, this is a solid, this is where it's boiling, now it's a liquid, now it's evaporating, now it's a gas. So what's cool is that all substances have the same shape. But if this were the graph for, let's say it's water, right? Any thoughts by raise a hand how the graph for iron would look different due to its specific heat? Zach?
Would it look steeper?
Why?
Because it heats faster, so it doesn't need to remain in each going up as well.
Yep, so the slope of our line is going to be steeper because it changes much quicker to get to a higher temperature. Well done, Zach. I was confused for that. So, I thought that was a cool connection. So, okay, questions before we try another math problem here?
Oh, man.
Okay, so the next part we're going to calculate, so the first part was Q. The next part, which is really the end goal, is getting to what's known as the delta H, or the enthalpy of the reaction. Okay, now the difference of the two and why delta H, I guess you could say they both have value, but there's more benefits to getting to delta H is Q. The value of Q is going to vary by experiment. We're going to do a calorimetry lab next week, and every single table is probably going to get a different Q value because you'll use a different amount of your substance. They might use 4.8 grams, you might use 5.1 gram, right? And that's going to change how much heat comes out. But delta H, because it's a ratio of the heat per mole that was used, stays constant. So delta H for a reaction is always the same. So even though you all will calculate different Q's, in the end you should all get the same delta H. And so that is where it's kind of beneficial because it helps you really see the benefit of it. In our lab next week, we're going to be testing different substances for you to identify which one would work best as a hand warmer, right? But you can be deceived because something could have a really big Q, but if I had to use 100 grams of my sample to get that big Q, probably not a practical hand warmer, right? If I have to make it this big versus something that I don't need very much of in the end. Now, if you want to make a note here, this is not on your formula sheet. I'm sorry, it's not my fault. I don't know why they like just leave off a few. So this is not on your formula sheet. The nice thing is when it is often asked, they will remind you of its units, which can kind of help remind you of what you're doing, because kilojoules is heat, Q, and then mole is mole. But if you want to make note of that, it isn't on the formula sheet. So, all right, let's go ahead and try solving for delta H using the exact same question. So it's on a different page, but if you want to make notes yourself, this is the exact same question we just solved minus, what is it wanting us to find this time? Enthalpy change, which is delta H. Okay, so it's all the same, just now instead of Q, we want to find delta H. So delta H is Q in the unit of a kilojoule over the moles of the reaction. And pretty much every time on the AP exam, when you're finding delta H, the question prior will be you found Q. So like A is find Q, B is find delta H every time. All right, so being that it's the same problem, we found Q from our problem before. What was Q? Right, so if you want to make a note, right, we found that on the page before. Now we do need to do a quick unit swap or switch. So this is in joules, but to be in delta H, they want it in kilojoules. Does anyone remember the relationship? 1,000. Yeah, so we're going to divide 1,000 joules for every 1 kilojoule. So we get 2.717 kilojoules. A joule, by the way, is a pretty small unit of energy. So it's normal for joules to be a really big number, just by the way. So like when you're doing your homework, if you get like an answer of like in the hundreds of thousands for joules, it's very common. Okay? All right, so I found this. Kilojoules. Now the bottom is we need to find the moles from the reaction. Now the difference here is when you're finding moles, it should be based on the limiting reactant. So it's not total. The reason being is, once I run out of wood, my fire is going to stop. And so we want to only focus on which one got used up first. Right? In terms of a wood, the other reactant is oxygen, which there's always going to be plenty of oxygen surrounding my fire, right? Okay, so go to the equation, and we need to see what are the two things that reacted, and see which one's going to run out first. So what are the two things we're pouring together? So we have HCl and NaOH. How much HCl was used? 50 mils of a 1 molar. How much NaOH was used? 50 mils, and they didn't tell us its molarity. It's supposed to be 1 as well. I don't know where that got left off. So in this case, we have the same amount of both. So then the next step is to look at the balanced equation and see if you have the same of both, right? So I'm using the same of this and the same of this. Which one's going to get a run out first based on the balanced equation? So the balanced equation, I didn't put it on this slide, so if you want to write it above this problem, is NaOH, and this would be given, is reacting with HCl, ends up making water and sodium chloride. It's a really fancy way to make salt water. So since I have the same of both of these, right, so I have 50 mils of a 1 molar, and 50 mils of a 1 molar. Since the balanced equation is 1 to 1, because it's already balanced, neither are technically limiting because they're both going to run out at the same time. So I can just use one of them because it's going to be the same. If hypothetically, just maybe on like a problem you're going to do in a second, right? Like if there was a 2 here, which one would run out first? Good, the HCl, because you need twice the amount of this to this, and you're starting with the same. So like there's one on your homework where I think it's a 1 to 3 ratio, but you're starting with the same amount. So keep that in mind. Does that make sense? Okay, so I need to convert milliliters into moles. I have molarity. So here's how I choose to set it up. So I'm going to start with my 50 mils, and I'm going to convert that into liters. So there's 1,000 milliliters in every 1 liter, because I can use liters to cancel out for molarity, because molarity is moles per liter. Sorry, give me a second to write that. Okay, so we know the molarity is 1, so it's 1.0 mole per liter, so that just came because of the molarity that was given. So if the molarity was 2, then we would have had 2 over liters, or 3 over liters, or whatever. So in the end, I find that I have 0.05 moles that reactant. Questions how I got my moles? Alright, so now take that, plug it in up here, divide and get an answer of 54. Questions on where it got something from? Yeah.
So, if you were to have an unbalanced equation, like if you had the 2, how do you get the 2? Like, does it tell you that it's 2, or just, I don't know how to do
Yeah, so like the equation when it's balanced will have like those numbers. Does that make sense? So like the problem itself, like, you know how we like balance chemical equations?
Yeah.
So it'd just be, the equation would be balanced and not 1, 1, 1, 1. It'd be like 1, 2, 2, 1.
So if like there was like 200 milliliters of 5, one's like this.
Yeah, so if by chance these aren't the same, then you gotta convert them to moles to then like compare which one will run out first. That kind of makes sense. We'll do some more examples here, so it might help maybe if we just see more scenarios of it. Okay, what's my unit on this number? Yes, so it's kilojoules, this is per mole. Now, final piece. Oh, we're squeaking going on. The sign. The sign of delta H needs to match whether the reaction is endo or exothermic. So the final piece is you need to make sure, and a lot of problems will say, like on the one we'll look on in a second, it will say, make sure to include the appropriate algebraic sign, right? So the sign of delta H needs to match if it is endo or exo. Where endo is always negative. Oh no, I said it backwards, sorry. Exo is negative and endo is positive. So what should be the appropriate sign for our experiment? Remember how you crossed your arms earlier? It's the same problem as before, right? There's a few ways you can think about it. Number one, it's actually always going to be opposite of what you get. There's always a sign flip because of the idea of going from the calorimeter to the reaction. So if you want to like remember that, like, okay, when I get to delta H, I always have to flip the sign. If it's positive, it's going to become negative. If it's negative, it needs to be positive. I prefer just once again to think about it logically of like, what should this represent and make sure it matches. Because I'm just not a fan of just memorizing to flip something without really understanding why. So, okay, questions before we try a new one with your table for some smileys. Lindsay.
So how do you find if it's endo or exo based on the math problem? Because the way I figured it out was I just read the question.
That's really it. Yep, it's just since the temperature went up, we know it's exo. Yeah, that's how I did it. So the mathematical way is the fact of like the Q we calculate in problem 1 technically always switches signs when it comes into delta H. So Yeah, good question, Kenzie. I was on my face with that. Any other questions? Okay, another thing I read on, I haven't gone through all of them, but some of you requested, was just more practice problems in class, as many as we can do. And I realized for this unit, I didn't have a practice problem. So we're gonna do one. If you want to just do it on like the next blank page, because we have some blank pages in our
Or
notes.
we should do a homework assignment. I mean, a homework question.
Well, so, yes, but in terms of like, so there's kind of like this thing called like scaffolding and learning, right? So like we did one together, and the next best step would be like you do one like here, and then your homework's an opportunity for you to like make sure you
What
got
if we
it.
just had it be like a homework assignment instead of doing a different assignment? So then
But then you don't have an opportunity to practice it on your own.
But we have 3 AP classrooms and a homework assignment.
But they're not about this problem, this like this specific skill. Does that make sense? We could go with that in the future. If we had a homework where there was multiple of the same type of question, that totally, I'll look at that. That could do with it. But that's why, is because if we do them all together, then you might build up a false confidence of like, I know how to do this. But it's because you did all of them with help. So. Okay. So I'm gonna just put the question up here on the board. You're gonna work as a table. I'm gonna give you about 9 minutes. There's 2 questions. So the first one is finding Q. The second one is finding delta H. Okay? Now, this was something I realized last class that didn't work out, so it's gonna look a little weird. Maybe let's do this first. So the first part, this is actually a question is stemming off of this same FRQ. So this actually was on last year's AP chemistry test. And this was part F of the question. Okay? Part G, and I think it's GI and GI2 that I'm about to show you, are going to have you calculate the Q and the delta H. So first off, looking here, we need to, because this chart's not on my next slide, we need to find the delta T. So everyone, talk to the table group, look down on this paper, what is my change in temperature, and then I'll show you the next slide. Alright, is everybody ready if I switch over to the question? Okay, here, so there's 2 parts, part I and I2. So find Q, find delta H. You can work as a table group. Once you have your final answers, raise your hand and I'll come give you a stamp of smiley faces that you got right, okay?
I gotta lean forward and I go
That equals Q, right? What do you think, like, it has you
4.0. I mean, I did 4.0.
Anyone notice when they stop losing their heat? I don't really know how long these are designed to stay on.
It's 4 minutes.
Didn't make it possible to find the moles of blend. I wrote down some information in black that was on the next slide. Does that help you?
It's okay, me too. Coming back from Christmas, I'm hard on the brain.
Once you think you have them both right, raise your hand, I'll come check. Or if you need help before then, let me know.
Oh, yeah.
He was right.
Yeah, that's right.
I wrote in black some information about the first line. That's good. You could put something else. Maybe it's because you thought it was like the previous maybe I'll finish. Hey, by the way, I wrote some information in a black marker that was on the slide with the data table. So that will be important in you solving part 2. But it didn't give you a list. What do you think? What would you want in the molarity form? To find the moles of that? Can you find the moles of the other two? Doubt it. So, one, I'd say it's kind of safe to assume if it feels impossible to find the moles of one, that it's not your question. So find the moles of the other thing is to kind of consider the difference between 50 milliliters of substance and a gram. Like if I put that gram in there, the gram's going to react. There's still going to be 50 milliliters. So you also kind of all right. We figure our error. Oh, good. And
You're going to run out of
That's 40. I'm gonna make sure every change code you want, you need 100 for one. It's 100 grams per mole. Because calcium weighs 40 grams, the carbon weighs 12 grams per mole, and 3 oxygen would weigh 48
I don't know what you're talking
grams per mole. If we have 1 gram, then we have 100 grams per mole.
All right, what do we come to?
It is negative.
All right, try. Okay, I could maybe give like 1 more minute, if you guys want 1 more minute, but then I want to give time to go through it. So do you want 1 more minute to check and then we'll go through it together? Let me set this, otherwise 1 minute will turn into 5. Yes!
It kind of was, but I thought there'd be like slides that I need to send you, but totally hard.
Oh, how do you insert it? This, the grams units, the grams per
Hard because it's like a lot of people understand, but it's just like, you know,
So we turn grams into units faster. Well, no, it's not divided by 1,000. That's
And I took two, and then I ended up sucking. It happens. It happens.
Yeah. Well, it's not negative. Yes, negative. I don't care enough. I already have like the equivalent of basically 10% worth of smiley faces. So
Make sure everybody subscribes. Check and subscribe. Blah blah blah.
It's just a Letterman jacket.